Now we want to contrast cache coherence with memory consistency. Cache coherence deals with the ordering of operations to a single memory location, while memory consistency deals with the ordering of operations to different memory locations. Cache coherence is implemented in hardware using various cache coherence protocols. Hardware alone guarantees correctness. It doesn't have to rely on the software, but the performance varies. Sometimes cache coherence algorithms impose a performance overhead. With memory consistency, on the other hand, that's tackled by consistency models, which are supported in hardware, but software needs to conform to the model. That is to say, sometimes the software needs to tell the hardware what are the synchronization variables in order for the program to work correctly. In cache coherence, all protocols realize the same abstraction. That means that a program that's written for one protocol can run without change regardless of what kind of coherence protocol the hardware uses. But with memory consistency, that's not true. Different abstractions are supported by different consistency models. In some cases, programs can run without change. In other cases, compilers must be aware of the model. They might not be able to reorder certain operations because they would produce inconsistent results. And then also, in some models, programs need to be very careful in using shared variables. They need to explicitly synchronize the operation of certain variables, for example. Now, in dealing with consistency, there are two different kinds of consistency. The simplest to deal with is sequential consistency, where multi-threaded code for uniprocessors automatically runs correctly on multiple processors because the system sees all of the operations in the same order. That is to say, every shared read or write completes globally in program order. Completes, when I say completes globally, that means it's seen to happen at the same time everywhere. The other kind of consistency is relaxed consistency models. Now, sequential consistency is basically infeasible on large systems because the performance is so bad. You've got to wait until every operation completes to do another memory operation, and that's throughout the whole system. So as your system gets large, you just can't afford to wait that long. So in that case, what's used are relaxed consistency models. And in this situation, multi-threaded code needs to be ported to run correctly. Like a lot of times you have to annotate which variables are synchronization variables and which could get reordered without problems. And that requires additional instructions, for example, memory fence instructions, to ensure that the operation before the fence actually happens before the operation after the fence. Okay, so let's consider the requirements for cache coherence and memory consistency in order. With cache coherence, do we need caches? Yeah, I mean, you could get rid of the cache coherence problem if you didn't have caches, but you wouldn't get very fast data access and your processors would run so slowly that it's actually infeasible. You also need caches to reduce the bandwidth needed across the bus or interconnection. If you didn't have caches, every single memory reference would have to transit the bus or the interconnection network, and the overhead of doing that would be just too great. So you want to keep them on the processor side of the interface, keep them on chip, so to speak, in cache whenever possible. Sufficient conditions for coherence involve the following. First of all, we say that a particular processor makes a request, a read or a write request for data. And if it's a read request, the write propagation condition, which is one of the two conditions for coherence, says that a read to a particular location must return the latest value that was written to that location. So that's propagation. The other condition is write serialization, which says that two writes to the same location are seen in the same order by everybody. In other words, if I see W2 write 2 after write 1, you shouldn't see write 2 before write 1. That implies that there needs to be a global ordering of memory operations to a single location. Now let's remember, cache coherence deals with a single location. So we've seen that there's a need for write serialization. The question might arise, is there a need for read serialization as well? And the answer to that is no, because two reads to the same location can occur in either order, and the same value is returned by both unless there's an intervening write. So you don't need to worry about the ordering of reads. Now, for coherence, we have to have our system obey the following principles. With uniprocessors, it's pretty easy because there you only have one processor plus I/O devices writing to memory. So in order to ensure consistency, you can say, well, I'm not going to cache any write buffers. And then if I don't cache any write buffers, I don't need to worry about the possibility that some memory is cached when I end up doing a write to memory. You could have uncacheable operations. Particular writes can't be cached. They need to go directly to main memory. You could flush pages before a write occurs to them. Or you could require that all I/O data gets stored in the cache. And all of these solutions will solve the problem for uniprocessors. But with multiprocessors, you can't do something like this because you can't have, let's say, all data going through the same memory, all data going through the same cache, all data going through the same memory, because there's just too much data, too many processors. You can't have all the processors write to the same memory module because memory just couldn't keep up. So it's performance critical and a hardware solution is required. When I say that each memory has to see, or each processor has to see the latest write in order, you can't really say what latest means. I mean, latest is relative to a particular vantage point, right? Because there's a time, there's some kind of latency between the time that an event occurs in a particular location and it's seen in any other location just because of the speed of light. So latest write is somewhat ambiguous, but if we have a consistent memory, we make sure that all the writes to the same memory are seen in order, and that solves the ambiguity, at least for the purposes of the consistency model. What we care about is that any write that's propagated needs to go everywhere in the same order, and then our synchronization algorithm will define what latest means. So, in summary, shared memory with caches raises the problem of cache coherence because writes to the same location need to be seen in the same order. But even if we ensure that, we haven't solved the whole problem. Writes to different locations must also be kept in order if their order is being depended upon for synchronizing tasks. There are certain writes that you don't need to see in order, writes that are, for example, local to only one process. But anything that's shared and might be used by one task as a way to synchronize with another task needs to be seen in order all over. This is called the memory consistency problem.